do an acknowledgement to country, and Farmers for Climate Action acknowledges the traditional owners of the land on which we're standing and broadcasting from today. And we'd also like to acknowledge the traditional owners of the land of which the attendees are standing in. We pay respects to their elders, past and present, and to their emerging leaders. And I'd just like to note that I'm broadcasting from Wiradjuri country today, which is where I live. So thank you. Now, we'd like to explain just a bit. Farmers for Climate Action, as you probably know, is an organisation of farmers. We try and provide quality science-based information to our farmer members, and we like to do that in a safe environment where open discussion can be conducted without people feeling threatened or not being respected. So with that in mind, we'll keep doing that for our members. Anybody who's not a member, feel free to go to the website and fill in the details and join us, and we will provide you with what we can when we can. It doesn't cost anything, and it helps us build pressure on taking action on climate change. So without further ado, I will introduce Dr. Cathy Waters, our speaker today. Now, Cathy is the Principal Research Scientist and Leader of Climate Research in New South Wales DPI. She manages a high-performing team of scientists working across both applied climate science and industry practice space. Current research themes include the science policy interface, holistic approaches to climate change, impact assessment, and abatement potential from the agricultural sector. Her current research program is focused on carbon, that is emissions reduction and sequestration, and energy, supply and demand, and these themes under the New South Wales DPI Climate Change Research Strategy. This research aims to create opportunities to increase farm business resilience through the creation of additional income streams from carbon farming and cost savings through energy efficiencies and transition to clean energy. Cathy is also co-developing the New South Wales Primary Industries and Productivity Abatement Program with the Department of Planning, Industry and Environment, and is developing new R&D areas, including whole farm carbon management. So I think everybody will find her depth of knowledge to be pretty extraordinary. Cathy has had more than 25 years experience working as a rangeland ecologist in sustainable grazing management, policy development, and addressing ground cover and total grazing pressure management. So without further ado, I shall hand over to Cathy to present today's presentation. Thank you.
Okay, so thanks, Peter. So in this presentation, I'm going to give you a bit of a mixed bag, if you like, of some past research that I've undertaken within New South Wales DPI with Susan Orgel, who's also in New South Wales DPI, who leads the soil carbon research in our organisation. A little bit of ongoing research that we're doing as part of the New South Wales Primary Industries Climate Change Research Strategy, particularly acknowledging contribution of Dr. Bin Wang from my group, who's based in Wagga, and Jonathan Gray from DPI, so from Department of Planning, Industry and Environment, with some of the modelling work that we've been doing with environment. And then touching on some of the new areas of work, as Peter mentioned, that we've been working on around the Primary Industries Productivity and Abatement Program. Look, I just put this slide in to sort of bring us back to a global context in our consideration of soil carbon and those sequestration opportunities, because the opportunities for sequestration of soil carbon and the quantum of abatement per se is often highlighted as this amazing opportunity. But what's not recognised and needs to be is the linkages between soil carbon and increasing soil carbon sequestration and land productivity and livelihoods and reversing land degradation and being able to sustainably manage landscapes and have more resilient landscapes into the future. And there's seven sustainable development goals that are really linked to soil carbon. So in this presentation, I'm going to go through some of the soil carbon modelling that we've been undertaking to really highlight some of these main drivers and to be able to, that determine soil carbon sequestration potential, and to be able to outline that what we've identified as the regional potential in New South Wales. So I really want to focus on grazing management practices and how that influences soil carbon, because that's a bit of a passion of mine. But I think with some of the research work that we've undertaken, it really illustrates really well some of these complexities about the spatial and temporal variation that there is in soil carbon. And then finally, I want to be able to talk about how we actually capture some of these opportunities with market and non-market abatement activities and these benefits going forward. So one of the fundamental questions that we had when looking at what is this potential for soil sequestration in New South Wales, and what is the feasible abatement that we can achieve, there were two things that we really needed to be able to do. We wanted to be able to really understand what the current stocks are and what the maximum attainable soil carbon might be in New South Wales. So that would give us an understanding of the quantum of abatement, and really be able to set these realistic, achievable targets for New South Wales. So it helps us to sort of manage these expectations. So we're really wanting to find out what the current carbon stocks were and how much realistic sequestration could be achieved. We also wanted to address some of those key uncertainties about the impacts of future climate change on sequestration rates, and what the magnitude of those impacts would be into the far future in particular. So the map on the right is an example of a digital soil map that was created in 2015. So we were looking at updating that map. So to create this sort of current benchmark map, if you like, of soil carbon stocks in New South Wales, and to look at these sort of broad regional trends, what we did was we used direct observations from soil carbon measurements that we made in the field, and they're highlighted there in those coloured dots in the green and the red. And we used a digital soil mapping framework to be able to predict the current and the future carbon stocks in New South Wales. So we created this map using a multiple linear regression model to derive stocks in the top 30 centimetres of soil based on these observations. And we had over 2,000 observations that were collected from 3 data sets: the state MER, Monitoring, Evaluation and Reporting Program within the Department of Environment, from the National Soils Carbon Research Program, and our Filling the Research Gaps program as well. So SCARP program and the Filling the Research Gaps more recent program. And about 80% of that data was used as training, and about 20% of the data was used as an independent testing to be able to create the map on the right-hand side. So you can see that the stocks ranged in the western areas to less than 20 tonnes per hectare, and then some spots, particularly on the coast, greater than 120 tonnes per hectare. We then wanted to be able to look at the potential sequestration with some management intervention. And what we looked at here was a change in 10% cover. So management practices that would increase or contribute towards a 10% cover would include changes to woody vegetation, so trees and shrubs, but also increasing ground cover layers, so the perennial grasses, or conversion of croplands to perennial pastures. And so what we found was, particularly some areas in the east, the cover levels were already really high. So you can see that in the eastern coastal fringes, where the yellow indicates the sort of low potential sequestration rate. So being able to use that stock benchmark map, soil stock benchmark map, we looked at that potential for that 10% cover change. And we found that there was a significant amount of abatement in some areas, so they were greater than 12 tonnes per hectare. But those sequestration rates really varied, and they varied from about 3.2 to 17.5 tonnes per hectare, depending on the environment regime. So a mean across the state was around 4.7 tonnes of carbon per hectare. So that sort of was amounting to quite a significant sequestration potential of in excess of 400 megatonnes of carbon, or 1,600 megatonnes of CO2 equivalent across New South Wales. So doing this exercise really allowed us to be able to look at the areas that had the highest sequestration potential, and that's sort of going to help us sort of prioritise future funding areas and effort in some areas. So not just where the highest sequestration rates are, but where there are potential to lose a lot of soil carbon. So this table really shows some of those estimates for soil carbon stocks in that top 30 centimetres, based on our multiple linear regression model for all LLS regions across New South Wales. So some areas, such as the Western Division, had the highest potential sequestration, even though they had the lowest rates, and that's because of the area that's covered by the Western Division. And some areas, such as the Central West and the Northwest, had high sequestration rates as well, around that sort of 290 to 320 megatonnes in total. So in this way, we were able to build a map for each LLS region and of the potential for sequestration with a 10% increase in cover. So this is a map at a 500 metre resolution, and the map on the right-hand side shows that mapping for the Central Tablelands area as an example. So looking at the extent of sequestration with that 10% absolute cover change, it made really clear some of these broad trends over the state, and this graphic really tries to illustrate or represent that change. So it shows the change across the rainfall gradient from dry to the right-hand side to moist and then wet on the right-hand side under different levels of cover, and the responses in terms of the categories of the soil types, so whether it was clay or sandy soil. So here you can see that the levels of sequestration increased under wetter climates with clay-rich, fertile soils that had higher levels of vegetation cover. So the next thing that we did with our stock map, our benchmark map, was using that benchmark map to be able to understand what the climate change impacts would be on the state going forward. So what we do is we look at multiple what we call GCMs, or global climate models, which provide a really large scale prediction of climate variables, such as major drivers such as rainfall and temperature, and we downscale those projections to a regional level. So the map on the right hand side shows the projected soil carbon stock changes in tonnes per hectare for each of the 25 GCMs that we use to undertake our impact assessment modelling. So this is for a period up to 2050, just for one emission scenario into the future. So we looked at multiple scenarios and multiple time slices as well. We use I put this map up here to really show that we use a large number of GCMs, so as we're better able to sample that variance in climate projections and make a more reliable prediction of that impact assessment. So using multiple GCMs really captures that variability in future climate projections. So this next slide shows some of those projections for for future stocks under different climate scenarios. So on the right-hand side are the changes, the mean changes in stocks under different climate scenarios. So on the top, we're looking at a low emissions scenario, and at the bottom, the worst case under a high emissions scenario. So, and this is into the far future. So the left two maps are to 2050 and the right two maps are 2090. And these relative changes are compared to historic baseline. So that baseline period was 1990 to 2019. So we can see that there are larger decreases in stocks were forecasted for in eastern New South Wales in the really high rainfall areas, so the North Coast, the Northern Tablelands, Hunter, and that really compares with some of the low rainfall areas of Western New South Wales. And the three panel slides on the left-hand side shows some of those changes on the North Coast and the Western Division and in the Central West. So small amount of changes, small amount of carbon stocks too in the Western Division on the middle panel, and much larger changes in the coastal areas. So summarising that, summarising the modelling work that we've done, the spatial distribution of the current soil carbon stocks in New South Wales really showed a decrease over time from east to west. And they're mainly influenced by big climatic rain drivers, but also the influence of vegetation cover type and soil type. So most of the important predictors for soil carbon stocks were the annual rainfall and the mean minimum temperature that we had. Now, none of these modelling really accounts for some of the compounding effects that we expect to see into the future. So series of droughts, sequential droughts, backing on to periods of high rainfall. So that sort of extreme events isn't counted in the modelling that we're doing. But the multiple GCM approach that we did undertake really allowed us to identify LLS regions that would experience the greatest decline in soil carbon under future scenarios. So the next part of the presentation, I'm going to run through some of the management influences on soil carbon based on some of the work that we've done in the rangelands. Now, whilst it's rangelands, I think some of the key messages that came out of this work really apply more broadly across the state. So I just want to be clear from the outset that we recognise that there are multiple ways in which management can influence soil carbon. We can add carbon-rich sources of organic matter to paddocks. We can use pasture and crop selection to be able to manipulate soil carbon, nutrient management, and we can address some of the major constraints, particularly around soil acidity and toxicity, to be able to influence soil carbon. But grazing management has been a tricky one, which is why I've sort of put this in there, because there's generally inconsistent results. So what we did is we took 3 sites across Western New South Wales. Now, we picked these sites because the land management of these sites were had been undertaken for more than 10 years, more than 8 years, in one case 10 years, where we considered the practice change was best practice, and we had worked on these sites for some time and had observed really high levels of ground cover compared to comparable paddocks outside or surrounding these particular sites. So we had 3 sites, and we used a paired contrasting situation to be able to compare the changes in soil carbon under managing the grazing intensity at these sites. So they're all slightly different, these sites, in terms of the management practices, clearly. The first site, as well, and some fundamentals about the vegetation and the soils at each of the site. So this site, the first site, was a floodplain, a grey soil, a vertisol, and it had extensive clay pans. And those clay pans had been treated through physical intervention, followed up by grazing management. So we were comparing rotational grazing in one side inside the best managed practice area compared to continuous grazing on the outside area. So grazing pressure and total grazing pressure in these sites was relatively low. There was some background kangaroo populations, but they weren't really high levels of grazing intensity. So what we found was that surprisingly, despite the really high and significantly high levels of perennial cover that persisted in the best practice area, that we didn't find any differences in soil carbon with depth. So the plot on the left-hand side shows the soil organic carbon percent at different depths through the profile. So again, we were looking at 30 centimetres, and that we didn't find any significant differences in soil carbon. But what we did find was there's quite a significant relationship that existed between soil carbon and the amount of perennial cover. So why didn't we find any significant soil carbon changes in this situation? So this grey soil is a self-mulching soil. They're called cracking grey clays, and there are really deep cracks, a number of metres deep in these soils. And those cracks may help, and that sort of mulching, self-mulching nature of the soil may help to redistribute the soil deep into the profile, so beyond the 30 centimetres that we looked at. It's a heavy clay soil, so the finer texture of that soil may also mean that the carbon is held in tight aggregates to protect the soil carbon from microbes and decomposition. In addition, at this location, the composition of the ground cover was really dominated. It was a really highly degraded site, so it was really dominated by short-lived perennial shrubs, and that sort of changed in more recent years to have a high perennial grass content. So there may have been a reduced contribution to below ground biomass accumulation, which might have influenced soil carbon and the organic matter supply to these areas. So the next site was one of two red soil sites that we had. I know red soils is a very general classification, but what we wanted to really look at this site was the effect of managing grazing intensity inside some fenced areas compared to unmanaged grazing intensity, where we had almost double the goat population on the outside, so high intensity grazing unmanaged on the outside. So, and we really wanted to compare, and we took some time being able to map the vegetation across these different areas that we were comparing. So our treatments really looked at three different vegetation types: a box community that existed on the broad sort of drainage lines, on the drainage flats, and a yarran community which existed on some of the drainage flats as well, but that consisted of really dense acacia species with clumps of turpentine. We also looked at the ridges that really were some of the least productive areas and were dominated by clumps of mulga. So what we found is there were significant differences between the ridges only. So, and they're indicated by those arrows, so E, and F, and that those differences really started somewhat deeper in the soil profile, so from about 10 centimetres down to that 30 centimetre, and there were quite significant differences in soil carbon. What we don't know is whether those differences were actually a sequestration or it was really reflecting a loss of soil carbon from erosion from outside those areas. But what we think is that in these red soils, we get a shorter turnover of soil carbon may occur where the vegetation in these communities respond to really small rainfall events compared to heavier rainfall events that are required on the grey soils. So the composition of the pastures is not seasonally dependent on really creating these organic supplies as it is on the red soils. And we found at these sites that there was a strong relationship with both perennial and litter cover and soil carbon. So the final site that we looked at was a similar red soil, but the difference was we were looking at the effects of trees in particular, and trees with grazing that was high density trees with high impact, high density unmanaged populations of goats and kangaroos, shown there on paddock I on the top. Paddock K looked at high density trees, but the area had been rotationally grazed for some time, for at least 10 years. And J was an area of high density trees, but with no grazing. We actually thought this was a conservation type situation because it had been sort of managed with no domestic stock and keeping wild, native and feral populations out of these areas. So this is a Balar pine community. So what we saw was quite significant differences in particular between the areas where we had high density of unmanaged populations and the high tree cover in that I paddock contrast. We had much higher levels of soil carbon with depth, and that's indicated by the black line on the right-hand side. But there was really no differences between K and J, what we're calling our conservation area, and the grazing, the area that had been grazed for about 10 years. So we suggest that really this absence of grazing and having no effect on soil carbon may reflect that the grazing intensity was sufficiently low, or the domestic livestock grazing was absent, and that soil organic matter accumulation may have been prevented or reduced due to grazing animals providing organic matter input through feces and nutrient redistribution, or the breaking down of vegetation and the litter through trampling, or the constant grazing of pastures and subsequent recovery and regrowth. So in summarising that body of work, it really shows that the amount of soil carbon that can be sequestered is really landscape dependent. So vegetation community, proximity to trees, the type of vegetation community, and the density of trees is really important. The amount of perennial cover might be important in some parts of the landscapes. That it's really clear that soil carbon is really a story about both sequestering carbon and avoiding the loss of soil carbon. That soil carbon can be moderated by ground cover, and particularly the amount of litter and perennial cover that is in some areas. That there is some temporal changes, particularly around the retention times of litter, that may also influence the level of soil organic carbon sequestration. So I spoke right at the beginning about the co-benefits of soil carbon, but the part of the study that I haven't sort of showed you is that we also looked at biodiversity, so both plants and animals at these sites, and that we found that the trade-offs between best management practice and soil carbon and ground cover and biodiversity and production were minimal, and there were these great advantages and co-benefits from managing for soil carbon. So that's some of the work that we had done in the past, and this is some of the work that's sort of emerging that we've been doing with our current program of work that we're just at a year from completing, but some of the future work that we've been undertaking as part of developing the primary industries productivity and abatement program that Peter mentioned. I put this slide in here because often we talk about carbon farming, and I don't think people understand the degree of land use change that has occurred in recent years across Australia. So this is a map that we created late last year about the Emissions Reduction Fund activities across Australia. So each of those activities are indicated with the different colours. Now, that activity and that extent of land use change has occurred since 2015. So it's a very, very short period of time. And what we're seeing is there's a lot of abatement that's been driven from vegetation management, and they're shown particularly in southern Australia, with the human-induced regeneration project shown there in blue, which is the allowing native vegetation to naturally recover and recruit. So you have a forest cover in these areas. So environmental plantings, which is tree plantings, there's a huge potential for environmental plantings, but there's been limited uptake because, as with the soil carbon methods, the projects have got key uncertainties around the trade-offs with existing land use and the production and the relative benefits and the value of carbon. So we've been doing quite a bit of work around different carbon prices and when those trade-offs could be minimised, and mapping where where economic carbon supply can occur. I just want to make a note that the soil carbon projects, there is a lot of interest in soil carbon projects, but there's only one soil carbon project that has been delivered to date. But the Clean Energy Regulator is currently working on developing a new method, a more workable method that's looking at potentially updating the two methods that we've got at the moment, which is a direct soil sample method and a model method which provides really conservative sequestration rates, and that's really limiting that ability to uptake that particular method. So some of the work that we did for the net zero plan and the Primary Industries Productivity and Abatement Program, or PIPAP, sits under the net zero plan. And so PIPAP is what it's trying to do is to really look at how we can drive abatement opportunities from all land tenures, including primary industries across New South Wales. And this is some of the graphic there shows some of the abatement potential, we think, under different ERF activities. Now you notice the quantum of carbon abatement, which is 20 megatons, is perhaps relatively smaller than what you would expect. We've been very conservative based on rates of adoption and those levels of soil carbon. So we've provided these conservative estimates really to be able to ensure that we're sort of not overestimating that potential, and that these estimates were really based on those conservative estimates the Commonwealth Government have in their default values for the soil carbon method. And we assumed only a 10% industry adoption rate, which we think that's a very conservative estimate as well. And one of the things that we did towards the end of last year, after extensive consultation, was we ran a number of what we called early win activities. And this was really to be able to identify specific project areas, and we ran three workshops around livestock emissions reduction, sequestration through vegetation management, and soil carbon sequestration. And we were looking at ways in which and the activities we could undertake to engage with abatement under each of those three key themes. The whole idea around these early win activities was really to be able to build confidence through the early delivery of abatement from New South Wales, and to be able to establish key partnerships and addressing key barriers that we identified through stakeholder engagement. So there were three major barriers that we felt could be addressed in some of these early win activities. And they were around the lack of information. So that's knowledge and capability for the industry to be able to run abatement projects and different activities, be they market activities through, for example, the ERF, or non-market ERF activities. We recognise that the ERF was well-established market mechanism, but it had its limitations. It was complex, it was difficult to navigate, and it only really looked at one activity at a time, but in agricultural landscapes, we think there are multiple activities, multiple management interventions to be able to look at abatement at a whole farm scale. One of the key barriers also was that the market structure at the moment really means that most landholders are essentially beholden for a carbon market developer to come to them, rather than them having control about abatement activities, whether they were market or non-market abatement activities. The second major barrier was around these sort of key uncertainties in understanding particularly farm scale trade-offs between existing land use and the vegetation-based ERF activities, and when a value proposition could be presented to a farmer. So, and there were key uncertainties around emissions reduction in livestock, in particular, the production impact on meat production, milk quality, for example, on some of the feed additives. And the third major barrier is really around cost and the high costs of participating and establishing projects and running projects through their cycle in the ERF. And particularly, it was highlighted that the baselining of soil carbon measurements for the soil carbon methods measured method had really high transactional costs that were really providing these sort of major uncertainties about the returns. So what we've developed is a new project that we're hoping to commence later this year, which is really looking at whole farm carbon management. And it has three key elements. There is a whole farm carbon advice and planning element, which really focuses on non-market abatement activities, a concierge service, which is really focusing on being able to help landholders navigate some of those complexities around the emissions reduction fund methods, and then an incentive program element as well that will be linked to both activities. So some of the key activities within the whole farm carbon planning component really looks at capitalising on hubs and networks, such as Farmers for Climate Action, and being able to deliver specific training and education programs and outreach activities around this non-market abatement potential. So managing abatement activities at a farm scale, looking at all options: vegetation, soils, livestock, energy. We think a really key element to this is it will be to undertake and to demonstrate to producer groups some of these activities. So where there are high levels of uncertainties around the production impacts, they'll be undertaken on research stations at DPI run around the state. They'll be supplemented through some commercial demonstration sites as well that will form satellite sites around some core sites. A major component of this element of the project will be looking at some of the tools and the products that we can develop for farmers to be able to quantify non-market abatement activities and to verify and to be able to help fine-tune some of the monitoring methods for some of the ERF methods. We think that a really important element of this is that this will be the first time that we'll be able to develop some protocols to capture these non-market abatement activities and connect those activities to the national inventory so they can actually be accounted for. And we'll do that by developing specific protocols. And so for soil carbon, some of those protocols may involve these established linkages between ground cover, perennial and litter cover, and remote sensed methods to be able to measure those changes, and really looking at avoiding the loss of soil carbon as well. So we will capture those non-market abatement activities through a carbon asset register, which will link to the national inventory. So the second part of of the project will look at really engaging landholders and undertaking what we call pre-project development on behalf of the carbon market developers. So those pre-project development activities are indicated there in blue. So looking at eligibility of land for different methods and some of the spatial opportunities mapping at a farm level, and estimates around the abatements, the potential of abatement. So a value and a risk assessment can be undertaken. We'll take those potential projects then to the marketplace through the Carbon Market Institute, or something similar as their marketplace that they have. And a key measure of the outcomes and success of this element of the project will be the number of projects that are established through the ERF or to the secondary market. A major element of the program is the incentives, but we think that will kick in the second half of the project, as we'll use the first half of the project to really design and tailor those incentives to what we learn from the whole farm carbon advice and planning and the concierge service. And just finally, I put this slide in to show where the whole farm carbon management really fits in terms of the on-ground abatement and its delivery, and the focus on agricultural production, which is a priority for PIPAP, because we don't want to switch land use from one activity to another. We want to be able to try and integrate abatement activities into the whole farm carbon management concept. So each of the red dots indicates some really some major initiatives that have been announced, or some that have been ongoing for a number of years, but most of them have been announced in the last 12 months or so. So we think that some of the major outcomes from the whole farm carbon management project will be that farmers will be able to make more informed decisions about carbon management, and they'll have the tools to be able to integrate abatement into the farm business, and they'll have access to industry relevant carbon advice and services. So we hope to expand those opportunities to allow farmers to earn extra income from carbon activities, in particular market activities, and to be able to help demonstrate sustainable land management practices. So we'll capture for the first time some of the non-market abatement activities that occur from the land sector, from agriculture, and be able to increase the access to the ERF projects. Okay, thank you.
Thank you, Cathy. Now that was very interesting, and it does show that there does appear to be substantial ability to sequester carbon if we put our minds to it and carry out best practice. I was interested in one of your slides there. It seemed to show the one with the trees, heavy tree cover and the grazing management. It seemed to show the heavy grazing with trees gave the most carbon. Am I reading that right? Or you had the ungrazed area, which was your conservation area with heavy tree cover, and you had managed grazing.
You're asking
no,
something
right.
about one of the conservation paddocks in that grazing.
Well, it was interest to me. It seemed to indicate from the graph that there was more carbon sequestered in the heavily grazed heavy tree cover than in the managed grazed or the ungrazed. Was that the right reading of it?
Yeah, that is the right reading. And there was really high stem density and very low levels of ground cover. So a lot of that soil carbon would be associated with the root growth from the trees at that high stem density. Yep.
Okay. So well, so at the end of the day, with what you've presented there, we should be able to determine a fair bit of this from remote sensing.
Yes.
With satellites and things.
Yeah.
So that might make the costs.
Yeah.
All right. So we have some other questions, and before I lose this one from Julia, how does a farmer get into the system with a project, particularly as a pilot study? Is that possible yet?
Yeah, so we're sort of working through, this is in the context of participating in the whole farm carbon management project.
The question was, how does a farmer get into a project,
Okay.
particularly as a pilot study?
Okay, so I assume since they're asking about a pilot study, they're referring not to the emissions reduction fund activities, but to what we're proposing with the whole farm carbon project. So we haven't worked through how we will call for expressions of interest, but it'll be some sort of process, but through networks. So we want to be able to use peer-to-peer learning and networks in groups to be able to show some of these non-market abatement activities. So we will be looking for expressions of interest for participation in that particular project.
That would be handy when that comes around. David has asked, how do bushfires affect carbon sequestration?
Yeah, well, they do, very much. So obviously, when you're soil sampling, we avoid areas that have been previously burnt because they just distort the results. But there, when the fires subside, there is a sort of initial fertility bloom and a growth. And some of that regrowth where areas have been cleared and the regrowth comes in actually sequester carbon in vegetation quite rapidly. So we see a rapid spike and a rapid rate of increase, particularly with biomass, soil carbon sequestration in biomass.
Now, Rowan has asked, does the 10% increase in ground cover that you talked about in the first few slides, is that just perennial pasture species, or is there a way for minimum tillage cropping systems to increase carbon?
Yes, so I assume that's referring to the 10% increase in cover. And looking at the potential for sequestration. Yes, so we think that 10% increase in cover can be achieved from multiple ways, and one of those is looking at a greater cover within cropping systems. But we would be looking at permanent perennial cover
in a cropping system. So you're talking
conversion of perennial crops, from crops to perennial pastures.
Oh, okay, yeah, not growing crops anymore.
Yeah, so looking at longer term, cover.
Yep, okay, no, I'm with you there. All right. I don't quite understand this question, but Julia has asked, why is it a non-market project? Can gain those benefits as well? Just a minute. Why is it a non-market?
Yeah. So what we term as non-market activities, say, for example, really small-scale abatement activities. So on-farm tree growth, so restoring or planting trees in riparian areas, restoring degraded areas through water ponding, water spreading, erosion control activities, enhancing individual single paddock trees. They're really too small to be able to, on their own, enter into the current market. So they don't have enough scale of abatement to become a viable project. So that's what we're terming non-market abatement activities.
Right. Now there is another question from Andrew Robinson. He wants to know, is the current measurement to ground to 30 centimetres, which is what you've done? I guess he's asking, is that the only measure, or do they measure deeper? Or
yeah, that's a good question. So I haven't been involved with looking at soil carbon deeper into the profile, but there is a whole group of work that's been done in that area. I guess the only thing is that the 30 centimetres is the area where we think that the management activities will be able to influence that in a relatively short time frame, and that's the standard measure at the moment, 30 centimetres.
Right, 30 centimetres, that's fine. Now James has asked, can you briefly discuss the role of glomalin in retaining soil carbon? Glomalin, GLOML. Yeah, right.
I'm sorry, I'm not aware of that. Yeah.
Okay, no, we'll leave that one. Somebody's asked about the topic of acid soils. Yes, Jennifer, that will be on the 13th of May. So that's another 2 weeks away. Now, Emily's asked, there are lots of studies on carbon abatement and rotational grazing that seems to show minimal results for soil carbon. Do you think that rotational grazing actually has significant effects on soil carbon, or that perhaps the sequestration rates are too low to see in the short-term studies?
Look, it's a really good question, and it's a golden question. You're categorising, all the different grazing management activities and the types of management practices that occur into this is rotational grazing, this is continuous grazing, is problematic. So a lot of the responses in the landscapes really are dependent not just on the vegetation and the soil's capacity to sequester carbon, but also on the historical management practices. So we see areas that are highly degraded. We see the greatest rates of increases in soil sequestration. So we do see very varied results, and there is little unanimity in the literature. And there are a number of published publications where we're incorporating long periods of rest, and the definition of long varies as well, and allowing pastures to recover does result in certainly increased amount of litter and biomass, ground cover, which presumably will feed into that soil carbon as an input to the soil carbon. But there's a lot of studies that have not shown any differences. So I think that there's a couple of things that are going on. It's this complex melee of different management practices, and trying to simplify them into different categories, but also the level and the intensity of soil sampling, and how that is linked to the spatial and the temporal aspects of that variability in soil carbon. So it is really complex to measure soil carbon, which is why the default method in the current emissions reduction fund, the soil carbon method, is so conservative because there's a high degree of uncertainty around the ability to be able to detect those changes and retain that soil carbon.
Very good. And we might make this the last question because we're coming up on the hour and we've got a few little other bits and pieces to do yet. Andrew has asked, were dung beetles a significant contributing factor in grazing sequestration systems?
Okay, so I can only talk about the results of that project. So I've not worked on dung beetles, but aware of what MLA have been doing in that area. So we did look at invertebrate diversity on all of our sites. Surprise, surprise, we found a lot of ants, but we didn't find any dung beetles at all on any of our sites, despite really high levels of dung in some of those areas. So we did note that there were a high degree of, when you're categorising invertebrates, there are a high degree of invertebrates that were predatory in nature, so they were feeding off other invertebrates in terms of the composition, rather than vertebrate groups, broad groups that might be more heavily involved with churning over the organic matter in the soil.
Okay, well, thank you, Cathy. That's been a very interesting talk. And for those that want to go back over it, it will be up on the website. And thanks all our attendees. I hope you've got a lot out of that discussion. And thanks most importantly to Cathy for the informed and comprehensive discussion on carbon potential in New South Wales, at least, and probably across the rest of the country. So thank you all for attending. I don't think there's anything else I can inform you about other than most of this will be on the website in some way, or if you want to contact us, feel free to ring. So thank you very much, and we'll see you on the 13th of May for our acid soils webinar.
Thanks, everyone. Thanks, Cathy.
Thank you.